In this video, I'll be explaining how the Maillard reaction occurs when cooking an egg. The Maillard reaction is a chemical reaction that gives browned or cooked foods its distinctive flavor. So first I'll be cooking an egg on a fry pan, and we will observe what type of physical changes occur during the cooking process and what types of flavor or scents that the egg gives off. And afterwards I'll be explaining the chemistry behind why the color change and the scents occur.
Now I'm gonna put these eggs on the pan and we're gonna see how they cook. So right now they're not cooked, so you can see that they're all liquidy, but as the heat gets through the eggs, the proteins in the eggs denature, and the proteins slowly start to make bonds with each other again, and they start solidifying. So we can see that the eggs slowly becoming more and more solid. So you can see that it's getting cooked. I'm just gonna wait until the bottom gets a little brown. So we can see that you see the browning on the eggs, which shows that the Maillard reaction occurred. And we'll see in the next clip of the video that this browning and the scent is accounted for by a compound called melanoidin. And yeah, I'll be going over the chemical mechanism as to how melanoidin is formed.
The Maillard reaction occurs between a amino acid. In this case, I have specified a generic amino acid with this R group, and reducing sugar. In this case, it has an aldehyde group, and I have, to simplify things, I have indicated it as R2. So for the first step is that the amino acid, this amine group right here, the lone pairs act as the nucleophile, and it attacks this carbon center right here, and these double bond electrons move up. The reason as to why this carbon center acts as an electrophile is because it has a partial positive charge, and that is because this oxygen withdraws electron density. And in this nucleophilic attack forms a tetrahedral intermediate right here. And the next step that happens is that the lone pairs on this oxygen right here take a proton from this amine group, and these electrons drop down to the nitrogen. So this is proton transfer. And in the next step, the same hydroxyl group that just got protonated grabs another proton, a free proton from the environment, and this activates the hydroxyl group and makes it a good leaving group. Then in the subsequent step, these lone pairs on the nitrogen move towards this bond, and then the hydroxyl group, or now it's the H2O water group, it gets eliminated, and the byproduct is water. Then in the next step, a base comes and takes this proton on the nitrogen, and the electrons from the bond move on to the nitrogen, and this deprotonation forms a N-substituted glycosamine, which is an amine. Once this imine is formed, this undergoes an imine-enamine tautomerization. So how this occurs is that the lone pairs on the nitrogen first attack this hydrogen, and then these electrons go here, and now that nitrogen is protonated. Then a base comes deprotonate this carbon, and these electrons move here, and then subsequently the double bond here move towards the nitrogen, which results in the lone pairs ending up on the nitrogen, and that gives the nitrogen a neutral charge, and it forms the enamine in 1,2-enamyl. Then what happens is a keto-eno tautomerization. So first, the lone pairs on this oxygen drop down, which forces these double bonds to attack this hydrogen, and the electrons move to the base. And this results in the formation of a CH2 group, which is shown here. Then this positively charged OH group oxygen is not very good at carrying positive charges. So a base comes and deprotonates this oxygen, which results in the lone pair or the electrons from this bond to move down to the oxygen. And now the oxygen is neutrally charged, and it results in the formation of an amidori compound. These tautomerization events are collectively known as the amidori rearrangements, and this amidori compound can react further to produce melanoidin, which is seen here. This is just a general structure, but melanoidin, as mentioned earlier in the video, is known to be a brown Maillard reaction product that is responsible for the scent of foods. Melanoidins are only produced when the food is cooked, which suggests the need of heat in the reaction. And as observed throughout the reaction mechanisms, there are lots of steps in the reaction that require or that are reversible. So heat is necessary for these reactions to proceed in the forward direction. So in a given type of food, rather than having just one type of melanoidin, there are different types of melanoidins that interact with one another to create a scent or flavor. So foods have different combinations of melanoidins, and this is what gives rise to the different types of scents and flavors in food.